Welcome to the training program for Management and Strategy Institute's Certification in Error Proofing Techniques. Introduction to Poka-Yoke. What Poka-Yoke means and its origin in lean manufacturing. Poka-Yoke is a practical approach to design work, so that errors are either impossible or immediately visible. It is a cornerstone of lean because it shifts quality from inspection after the fact to prevention at the source. In this training, you will learn what the term means, how it emerged inside Toyota's production system, and why prevention changes the economics and culture of quality. What Poka-Yoke means. The Japanese words poka and yokaru translate to inadvertent error and to avoid. Put together, Poka-Yoke means mistake proofing or error proofing. The intent is simple. Build natural safeguards into products, tools, and processes so a normal human slip does not become a defect that reaches the customer. Poka-Yoke solutions are usually small, specific, and practical. They guide the worker toward the correct action or make the wrong action impossible. A good Poka-Yoke is inexpensive, easy to maintain, and does not rely on perfect attention or heroic effort. It respects human limits by shaping the environment so that the right outcome is the easiest outcome. Think about everyday life. A three-prong electrical plug only fits one way. A vehicle will not shift out of park unless the brake pedal is pressed. A website grays out the submit button until required fields are complete. Each example prevents a common slip from turning into a failure. That is Poka-Yoke in spirit and practice. Two clarifications help set the foundation. First, Poka-Yoke targets mistakes at the moment of work rather than errors discovered during inspection later on. Second, it does not replace the need for clear standards, training, or capable equipment. It reinforces those elements so they produce consistent results. Why mistake proofing matters. Defects are expensive. They consume time, materials, and goodwill, and the cost grows the later they are found. Prevention is less visible than rework or warranty claims, but it is far more powerful. By removing the opportunity for an error to occur, you collapse variation at its source, reduce reliance on inspection, and free people to do value-adding work rather than checking and fixing. Prevention also changes behavior. When a process makes the right way obvious and the wrong way hard, teams stop depending on memory or vigilance. Fatigue, distractions, and turnover still exist, yet their impact on quality shrinks because the system carries more of the burden. Origin in lean manufacturing. Poka-Yoke crystallized inside Toyota's production system in the early 1960s. Industrial engineer Shigeo Shingo, working with Toyota and its suppliers, observed that many defects did not come from complex technical failures. They came from small human slips that were predictable and preventable with simple devices or procedural changes. Shingo promoted a program he called Zero Quality Control. The idea was not to add more inspectors. It was to stop creating defects in the first place, and to reveal any abnormal condition immediately at the workstation. Poka-Yoke devices were the means to do this. They could be physical guides that only allow a part to be placed in the correct orientation, limit switches that confirm a step happened, or sensors that stop the process when a required component is missing. There is a well-known story from a Toyota supplier assembling small electrical switches. Workers occasionally forgot to insert a tiny spring, which later caused failures. Rather than add another inspector, the team redesigned the work. Operators picked up two springs from a small holder that triggered a counter. If the counter did not reach zero by the end of the cycle, the machine would not advance, and the missing step was obvious. A simple change removed a chronic defect mode. This pattern, repeated across plants and suppliers, low-cost devices, and clever work design that prevented the error or made it unmistakable. Originally, Shingo used the term Poka-Yoke, which means foolproofing. The language was softened to Poka-Yoke, to avoid insulting workers, and to emphasize respect. That change reflects an important lean principle. Errors are not moral failures. They are signals that the process can be improved so that ordinary people can do great work under ordinary conditions. How Poka-Yoke fits within Lean and Six Sigma. Poka-Yoke sits alongside other lean ideas that build quality into the process. Jidoka calls for stopping work when an abnormal condition is detected so the root cause can be addressed. 5S creates orderly, visual workplaces where the correct tool or part is easy to find and misuse is less likely. Standard work defines the best-known method, so that error-proofing can be designed against a clear baseline. Visual management communicates status at a glance, so problems do not hide. In Six Sigma terms, Poka-Yoke is most visible in the improve and control phases of DMEC. During improve, teams design solutions that remove defect opportunities. During control, those solutions are embedded in the process, so performance stays stable after the project closes. Statistical tools reduce variation that comes from process noise. Poka-Yoke reduces defects that come from discrete human slips and omission errors. The approaches are complementary. Characteristics of effective Poka-Yoke. Strong Poka-Yoke solutions share a few traits. They are simple to understand, easy to use, and hard to bypass during normal work. They act as early as possible, ideally, before an error can become a defect. They give immediate, unambiguous feedback to the person doing the work. They do not slow the process when the work is being done correctly. They are built with input from the people who perform the task, since those people understand where slips occur and what would help. Notice what is not required. You do not need a large budget, high technology, or a long project timeline. In many cases, a small fixture, a template, a color cue, or a change in sequence eliminates a large share of the problem. Creativity and empathy for the user often matter more than capital. Common misconceptions. Teams new to Poka-Yoke sometimes confuse it with inspection or with discipline. Inspection looks for defects after they exist. Discipline tries to make people concentrate harder. Poka-Yoke changes the system so the right action is the natural action. Another misconception is that error-proofing is only for assembly lines. Service work, healthcare, software deployment, and back-office processes all have repeated tasks where a slip can cause rework or harm. Digital forms can require fields before submission. Checklists can align complex handoffs. Scheduling systems can block double booking. The medium changes, but the principle stays the same. Types of errors and root causes. Not all quality problems are the same. Some begin with a human slip, some with a worn tool, and others with unclear or missing instructions. In this lesson, you will learn how to distinguish common sources of process errors, how to separate a mistake from a defect, what a zero defects mindset really means, and how these ideas connect to root cause analysis and prevention. Common sources of process errors. Human error. People make slips and lapses even when they know the correct method. Distractions, fatigue, high workload, and poor workstation design increase the chance of a wrong action or a missed step. Confusing screens, look-alike parts, and non-intuitive sequences also raise error rates. In practice, most recurring human errors are signals that the system is not supporting reliable performance. Examples include choosing the wrong item from a drop-down because the list is unsorted, skipping a torque step because the tool cart is far from the work area, or entering transposed digits because two fields are formatted differently. Equipment malfunction. Machines and tools drift, wear, or fail. Sensors go out of alignment, jigs loosen, and software versions fall out of sync. Measurement devices can be inaccurate or inconsistent, which creates false signals and hides real issues. Maintenance delays, inadequate calibration, and operating equipment outside its designed limits all show up later as quality problems. A press that vibrates beyond specification, a label printer that intermittently smears, or a scanner that reads some barcodes twice are typical pathways from equipment issues to downstream defects. Unclear instructions. Work becomes unreliable when the method is hidden, ambiguous, or scattered across several places. Missing steps, vague criteria, and version confusion create variation. Two supervisors may teach different sequences. A procedure may specify tighten firmly rather than a torque value. A form may require a code that is documented on a separate sheet that is often outdated. When the standard is not visible and precise, people will improvise. Variation then looks like personal failure, when it is actually a documentation and design problem. Quick diagnostic prompt. When you see a recurring problem, ask 3 questions in this order. Is the standard clear and visible at the point of use? Is the equipment capable and stable? Is the human task easy to perform correctly under real conditions. This sequence prevents premature blame and points you toward the most leverage. Difference between mistakes and defects. A mistake is an incorrect action or omission within the process. It is the moment someone selects the wrong part, skips a field, or sets a dial to the wrong value. A defect is a non-conformance in the output. It is the product shipped with the wrong part installed, the invoice sent with the wrong total, or the record saved with incomplete data. The distinction matters because a process can contain many mistakes that never become defects if the system catches them early. Good design prevents a mistake or makes it immediately visible and recoverable. Poka-Yoke focuses on the moment of mistake creation. Inspection focuses on finding defects after they exist. Your aim is to reduce the opportunities for mistakes and to intercept any that occur before they escape as defects. Illustration. In a medication room, a nurse may initially select the wrong concentration from a look-alike vial. That is a mistake. If a barcode scan that verifies the order blocks dispensing, the mistake does not become a defect that reaches the patient. The process contained an error, but the output remained correct because the system made recovery easy. The zero defects mindset. Zero defects is a commitment to meeting requirements every time, not a demand for perfectionism from individuals. It means you design work so that normal human variability does not create bad outcomes. The mindset shifts attention from sorting and rework to prevention at the source. It changes questions such as, who did this, into what in the process allowed this to happen, and how do we redesign so it cannot recur. A healthy zero defects culture is practical, not punitive. Teams celebrate the early detection of mistakes and treat them as process signals. Leaders invest in simple barriers that remove error opportunities. Success is measured by fewer opportunities for error and earlier detection when something goes off standard, not by how hard people try. What zero defects is not. It is not a promise that nothing will ever go wrong. It is a design philosophy that treats every recurring error as a solvable problem and prioritizes changes that prevent reoccurrence. Linked to root cause analysis and prevention. Root cause analysis is the structured way to move from a symptom to the underlying conditions that produced it. Poka-Yoke is one of the preferred countermeasures once you understand those conditions. The flow looks like this in practice. 1. Describe the problem clearly. Specify what happened, where, when, how often, and the impact. Avoid vague labels such as operator error. 2. Map the moment of error. Identify the exact step where the mistake occurred and the conditions present at that moment. Capture layout, lighting, labeling, software screens, and workload. 3. Identify potential causes. Use simple tools such as 5 whys or a cause and effect diagram to surface contributing factors in people, methods, machines, materials, measurements, and environment. 4. Test your thinking with data. Verify suspected causes. For example, compare error rates by shift, by part family, by workstation, or before and after a calibration event. Mini case. A distribution center had frequent wrong item picks among 2 nearly identical boxes. RCA showed the boxes were stored adjacent. Labels used the same font and color, and the pick screen abbreviated both names to the same first 8 characters. The team moved the items to separate bays, redesigned labels with bold color blocks and large part numbers, and changed the pick screen to show a thumbnail image and require a barcode confirmation. The error rate fell to near 0. The solution did not ask workers to try harder. It removed the path to the mistake. Key takeaways. Most quality problems begin with predictable conditions in the workplace. Mistakes are process actions that go wrong. Defects are outputs that fail requirements. A zero defects mindset focuses on prevention through design rather than after-the-fact sorting. Root cause analysis reveals where to focus, and Poka-Yoke converts that insight into simple barriers that protect the customer every time. 5. Select preventive countermeasures. Favor changes that make the wrong action impossible or immediately visible. Examples include physical keys that only fit one orientation, interlocks that require a step to be completed before the next can start, standardized screens that validate entries, color and shape cues that separate look-alike parts, and checklists embedded at the point of use. 6. Lock in the gain. Update standard work, train to the new method, and add a simple control, such as a visual check, a sensor, or a counter that signals abnormal conditions early. Poka-Yoke methods and techniques. Poka-Yoke methods can be grouped into three main categories: contact method, fixed value method, and motion step method, each designed to prevent mistakes in different ways. These methods are often supported by simple but effective devices such as sensors, guides, templates, interlocks, and visual cues. Understanding these approaches and seeing how they are applied in real-world settings can help you design systems that prevent errors before they happen. The contact method works by detecting errors through the physical attributes of a part or component, such as its shape, size, color, orientation, or pattern. It ensures that only the correct item in the correct form or position can proceed. This method is extremely effective because it is based on physical constraints rather than memory or judgment. Examples include a USB plug that only fits one way, a fixture on an assembly line that accepts only one size of screw, color-coded hospital tubing to prevent mismatched connections, and SIM cards with a corner cut off to avoid backward insertion. While the contact method offers high reliability and is easy to understand, it sometimes requires redesigning parts or fixtures and is less suited to non-physical tasks like data entry. The fixed value method ensures that a certain number of actions, components, or repetitions occur before moving to the next stage of work. It is especially useful for repetitive tasks that involve a specific count, such as inserting a set number of fasteners or scanning a defined number of items. In manufacturing, a counter might tally bolts inserted into a component, preventing the next step if the count is incorrect. In a maintenance environment, foam tool trays with cutouts reveal when a tool is missing, before the job is signed off. Medical laboratories sometimes use trays with fixed vial slots, so missing samples are caught before processing. This method helps prevent omissions and overprocessing, though it does not confirm that each action was performed correctly, only that it was completed. The motion step method verifies that steps are performed in the correct sequence, ensuring that no critical operations are skipped or rearranged. It is particularly important in processes where order is vital for safety, quality, or efficiency. Examples include digital forms that require certain fields to be completed before allowing submission, machine interlocks that prevent operation until guards are in place, and assembly systems that unlock only when the previous step is confirmed. While this method supports accuracy and safety, overly rigid designs can slow experienced workers or limit flexibility. Supporting these three methods are tools and devices that make error prevention more effective. Sensors can detect presence, orientation, or movement before allowing a process to proceed. Guides and locators help ensure that parts are positioned correctly, while templates and stencils standardize repetitive tasks such as cutting or labeling. Interlocks prevent progress unless specific conditions are met, and visual cues, such as color coding, icons, or designated zones, communicate status or guide actions at a glance. Real-world applications illustrate how these methods work together. In manufacturing, a car assembly plant reduced wiring harness errors by redesigning ports and plugs with unique shapes and colors so only correct connections were possible. In the service industry, a bank's online system began requiring 2 separate employee logins to authorize wire transfers, preventing both errors and fraud. In healthcare, a hospital prevented dosage errors by using color-coded syringes for pediatric medications and implementing barcode checks to verify patient identity before printing medication labels. In summary, the contact method focuses on preventing errors through physical design. The fixed value method ensures the correct number of actions are taken, and the motion step method enforces proper sequencing. When combined with tools like sensors, guides, templates, and visual cues, these methods form a powerful framework for mistake proofing. By applying them thoughtfully, organizations can reduce reliance on inspection and memory, leading to safer, more efficient, and more consistent processes. Designing effective Poka-Yoke solutions. Designing Poka-Yoke is about shaping work so that normal people using ordinary effort produce correct outcomes every time. The most reliable solutions are simple, affordable, and robust, which means they survive daily wear, turnover, and real-world variability. Start by stating the specific mistake you want to prevent, the exact moment it occurs, and the customer or safety risk if it escapes. With that clarity, you can design barriers and cues that either make the wrong action impossible or make it instantly visible. Simplicity is the first principle. Favor physical constraints, obvious geometry, and clear visual cues over training and reminders. A keyed connector that only fits one orientation is simpler than a laminated instruction card. A stencil that forces the label into the correct location is simpler than a place label here note. Simple designs have fewer failure modes, ask less of memory, and are easier to sustain when people are tired, rushed, or new to the job. When you evaluate a concept, ask whether someone could use it correctly, without instructions on a busy day. If the answer is yes, you are on the right track. Affordability keeps momentum high and encourages experimentation. Many effective Poka-Yoke devices cost little. Color sleeves that differentiate look-alike parts, foam inserts that reveal a missing tool, a jig that prevents upside-down assembly, form validation rules that block incomplete entries. Low-cost prototypes make it easier to test several ideas quickly. They also reduce resistance from stakeholders who worry about capital spending or downtime. A useful rule of thumb is to try the $10 fix before the $10,000 automation. If a cardboard template or 3D printed guide solves the problem, do not add software and sensors unless there is a clear benefit. Reliability means the solution works the same way under different conditions and is hard to bypass during normal work. The best devices detect an abnormal condition as early as possible and provide a clear signal that cannot be ignored. Reliability improves when you design for the extremes, not the averages. Consider glare on displays, gloves that reduce dexterity, vibration, temperature swings, and variation in part tolerances. Build the device so it still works when these factors are present. If the fix depends on a fragile alignment, tight calibration that is rarely performed, or perfect attention, it will not hold up. Frontline employees should co-design error-proofing. They see exactly where slips occur and which ideas will fit the job. Begin with a short discussion at the workstation about recent errors and what made them possible. Invite operators, technicians, nurses, or clerks to sketch ideas and build quick mock-ups. Ask what would make the right action automatic and the wrong action awkward. Test these mock-ups at the Gemba, rather than in a conference room. When people help create the solution, adoption is faster, the design is more practical, and you often discover simpler approaches than a distant expert would choose. Every Poka-Yoke needs testing and validation before full rollout. Define success in measurable terms such as error rate, rework minutes, first pass yield, or safety incidents, and collect a short baseline. Run a pilot in the real environment for at least several shifts or days to capture different users and conditions. Observe how people interact with the device. Look for workarounds, false triggers, and slowdowns. Track both effectiveness and side effects. If the station handles higher volume, ensure the device does not introduce a bottleneck. Where sensors or counters are used, check detection repeatability the way you would validate a measurement system. After the pilot, compare the results to baseline and collect feedback from those who used it. Refine the design, then retest until you see stable, repeatable performance. Avoid over-engineering and unnecessary complexity. A sophisticated solution that people dislike or cannot maintain will decay. Limit features to the minimum needed to prevent the error. Resist safety blanket layers such as extra alarms or screens that add clicks without adding protection. Design the device to be self-evident and to require no extra paperwork. Keep maintenance simple with standard fasteners, common spare parts, and clear cleaning routines. If the fix adds time, weight, or reach to the task, you may be trading one problem for another. Good designs are nearly invisible during correct work and only become present when something goes off standard. Integration into process workflows turns a clever idea into a lasting control. Update the standard work to include the device or rule, place it at the natural point of use, and arrange the workspace so the new flow is the path of least resistance. If an interlock must be engaged, design the sequence so it is engaged automatically as part of normal motion. Add the device to the control plan and FMEA so it is documented, audited, and monitored over time. Provide a short, on-the-spot orientation for new users, and a simple visual describing what good looks like and how to respond to an abnormal condition. Coordinate with maintenance to add inspections or calibration to their routine schedule. Finally, connect the Poka-Yoke to performance monitoring with a simple chart or dashboard so that leaders and teams can see whether the error has truly disappeared and whether the fix is being used. Consider a short example that ties these ideas together. A fulfillment cell often shipped the wrong variant of a lookalike part. The team first tried a reminder poster, which had no effect. They then co-designed a shelf insert with unique cutouts for each variant and added bold color blocks that matched the pick screen. The picker's handheld required a barcode confirmation before the tote would advance. The insert cost little and was cut from scrap plastic. A 2-day pilot showed the error rate falling to 0 with no cycle time penalty. Standard work and photos were updated, the insert was added to 5S audits, and maintenance agreed to inspect the insert monthly. 6 months later, the problem had not returned. To apply this module, identify one recurring mistake in your area and describe it precisely. Sketch a low-cost physical or digital change that would prevent the wrong action or reveal it immediately. Build a quick prototype, test it with the people who do the work, measure the effect for a week, and refine the design until it is simple, affordable, and reliable. Once proven, fold it into the workflow and the way you manage the process so the benefit endures. Case study. Designing a Poka-Yoke system to prevent incorrect order assembly in a fast food restaurant. The restaurant was experiencing frequent order accuracy issues during peak periods. Customers received the wrong sandwich variant, missing sides, incorrect drink sizes, or absent sauces. Quality checks at the counter caught some problems, but many escaped to customers, creating refunds, remake waste, and longer queues. A 2-week baseline showed an average of 1.9% incorrect orders, spiking above 3% during lunch rush, with the top 3 errors being missing fries, wrong sandwich variant, and missing sauces. The goal was to design a mistake-proof process that would prevent assembly errors at the source without slowing service. The team began by mapping the current assembly flow from order entry at the point of sale to kitchen display routing, hot hold pickup, fry station, beverage station, and bag sealing. Observation revealed common slip points. 2 orders were often staged side by side on a single counter with look-alike wrappers and cartons. The kitchen display compressed long orders, so clerks scrolled and lost context. Sides and drinks were prepared at different stations, which increased the chance that items were bagged for the wrong order. Bag labels were printed early and placed on the counter, which led to bag mix-ups when crew members rotated positions. Root cause analysis separated mistakes from defects and pointed to 3 dominant causes. Human factors were present in the form of cognitive overload, hurried motion, and look-alike packaging. Equipment factors included an aging label printer that occasionally skipped characters and a hot hold without location guidance. Instruction factors showed up as vague sequencing and no clear visual standard for what a complete order looked like at the bagging moment. Rather than add inspectors, the team chose to embed Poka-Yoke into the work so that an incorrect item could not be placed, an incomplete order could not be sealed, and 2 orders could not mix. The first design element used the contact method. The team introduced rigid, washable assembly mats sized to a single order, each printed on demand by the kitchen display system. When the cashier finalized an order, the system generated a large label with the order ID, customer name, and a simple layout graphic that matched the mat, positions for main items, sides, drinks, and sauces. The mat had shallow contours and cutouts keyed to common packaging shapes. A small fry carton only fit the small cutout. A large beverage cup only fit the large cup well. Sandwich clamshells were oriented with a corner notch that aligned to the mat silhouette, preventing rotated placement that hid the product code. Physical dividers between mats created a lane for each active order, so items from 2 orders could not occupy the same space. The second element applied a fixed value approach. The kitchen display presented each order as a countdown list, and the printed label included checkboxes that mirrored the list. As each item was placed on the mat, the assembler tapped the item on the display, which decremented the count. The system did not allow the bag seal label to print until the countdown reached 0. Low-cost aids reinforced the count. Sauce caddies used foam inserts with dedicated wells. If a sauce well remained filled when the order called for that packet, the missing condition was obvious to the eye. A tool rack at the fry station held a fixed number of salt packets per order size, so the assembler could not proceed without emptying the correct number of slots. The third element enforced motion step sequencing. The system required a scan of the order ID on the mat before any item could be scanned. Each hot item station had a simple barcode placard for each product variant, and each drink station generated a cup label with a scannable code for size and beverage type. The sequence was locked. Main items first, sides second, drinks third, sauces last, then bag seal. If an item was scanned out of sequence, the display flashed a correction and would not advance. If the order required 2 bags due to volume, the system created a second mat with a child ID and would not allow sealing of either bag until both child mats were complete. Supporting devices made the Poka-Yoke robust without adding burden. Pick-to-light rails were installed above the hot hold, so the correct slot illuminated when the assembler scanned the product code. Guides and locators ensured that clamshells snapped into a single orientation that exposed the product code to the scanner. Interlocks gated the bag seal printer, which would not print until 3 conditions were met. The countdown list was at 0. All required scans were complete, and the bag was briefly placed on a low-profile scale. The scale confirmed a weight band calculated from menu master data, with a tolerance wide enough to ignore ice variation in drinks, but tight enough to catch a missing sandwich or fries. If the weight was outside the band, the display provided a plain language prompt to check a specific category rather than a generic error. The team kept the design simple and affordable. Mats were cut from food-safe plastic and cost less than $20 each. The scan system used inexpensive QR codes printed by existing kitchen printers. The only new hardware was the low-profile scale and a light rail kit powered from the display. A cardboard prototype of the mat was trialed the same day the idea surfaced, which allowed quick learning about spacing, glare, and wipe-down time between orders. Crew members co-designed the final layout, moving the drink position to the upper right to reduce spills, and widening the sauce wells so gloved hands could reach easily. Testing and validation followed a straightforward plan. The store piloted the system on one assembly lane for 7 days, covering lunch and dinner rushes across all shifts. Metrics included order accuracy, average assembly time, and remakes per hour. Observers recorded any workaround attempts, false alarms from the scale, and delays caused by the sequencing rules. Early in the pilot, the scale flagged lightweight salads unexpectedly, which led to a quick update of the reference table to account for seasonal packaging. The team also adjusted the sequence so drinks could be prepared in parallel during extreme rush, but still required a final scan and weight check before sealing. Results were immediate and sustained. Order accuracy improved from a baseline of 98.1% to 99.6% during the pilot, with missing fries and wrong variant errors nearly eliminated. Average assembly time was unchanged because the physical guidance reduced searching and rechecking. Remakes per hour dropped, which shortened the queue during peak. Crew members reported less stress and fewer disagreements at the counter because the system made status visible and removed ambiguity about what was complete. After a second week without regressions, the system was rolled out to the second lane and the drive-through window. Integration into the workflow ensured the gains held. Standard work was updated with photos of a correctly loaded mat and a short script for the final check. The control plan added daily mat cleaning checks, weekly verification of the scale tolerance with a test bag, and a quick scan test each morning on the most common items. The fail-safe rules were documented in the restaurant's FMEA, so future menu changes would trigger a review of packaging shapes and weight bands. New hires received a 5-minute hands-on orientation using a dummy order, which proved enough to reach proficiency. The design avoided over-engineering by keeping technology light and making the right action the path of least resistance. There were no new passwords or handhelds. The mat visually organized work, the countdown list and scans ensured completeness and sequence, and the interlocked bag seal created a final gate that was hard to bypass. Exceptions such as substitutions and out-of-stock conditions were handled with a clearly labeled override button that required a supervisor scan and a quick reason code, which preserved flow while keeping data for later improvement. 6 months after implementation, the store maintained order accuracy above 99.5%, with the largest remaining defects tied to rare special requests that prompted further refinement of labels. The investment paid back in weeks through fewer remakes and better throughput at lunch. More important, the system respected human limits by shaping the environment so the correct build was obvious, and the wrong build could not quietly leave the counter. That is the essence of Poka-Yoke in a high-speed service setting. Sustaining and improving. Poka-Yoke measures. Sustaining error-proofing is a management practice as much as a technical one. The strongest Poka-Yoke fails if it is undocumented, unmonitored, or isolated from daily routines. This module shows how to embed each solution into standard work, track its performance over time, adapt it as processes change, and reinforce it with complementary lean tools such as 5S and visual management. Begin by documenting the solution directly in standard work at the point of use. The document should define the purpose of the device, the exact mistake it prevents, where it is located, and the correct way to engage it as part of the task sequence. Include clear photos or simple line drawings that show what good looks like and what an abnormal condition looks like. Add acceptance criteria that make pass and fail unambiguous, along with an immediate response plan that states who to notify, how to contain risk, and how to restart safely. Fold cleaning, inspection, calibration, and replacement intervals into the standard so upkeep is not left to memory. Use normal document control and versioning so every change is traceable, and keep the most current version at the workstation rather than buried on a shared drive. When new employees are trained, require hands-on demonstration and sign-off that the Poka-Yoke is used as written, not as a side note. Monitoring effectiveness should combine outcome measures with device health checks. Outcome measures answer whether the error is still happening, how often, and with what impact. Useful signals include first-pass yield, defect escape rate, rework minutes, customer complaints by category, and near-miss counts that were intercepted by the device. Plot these measures on simple run charts or control charts at the team board, so trends are visible and small deteriorations are detected early. Device health checks answer whether the safeguard itself is intact. Build a quick heartbeat test into daily startup to confirm sensors detect, interlocks actuate, templates align, or software validations still fire after updates. Track a few basic reliability indicators, such as mean time between failure, mean time to restore, false positive rate that slows work, and observed bypass attempts. When a defect appears, treat it as a process signal, verify the device functioned, confirm the standard was followed, and record the failure mode so the dataset grows useful over time. Sustaining does not mean freezing a design. Processes change as products evolve, volumes shift, regulations update, and technology is upgraded. Each change can create a new path to error or invalidate an earlier safeguard. Use a simple management of change routine whenever you alter layouts, tools, materials, software screens, or work sequence. The routine should ask whether any Poka-Yoke is affected, whether the FMEA and control plan require updates, and whether a short revalidation is needed. Plan small plan-do study act cycles that test an adaptation on one shift or one cell before broad rollout. Encourage teams to run short retrospectives when a safeguard causes friction, false alarms, or delays. Often a minor adjustment to geometry, label wording, or software logic removes a pain point without weakening protection. Capture each improvement as a one-point lesson, so learning spreads quickly to other areas doing similar work. Avoiding over-engineering is part of sustaining. The easiest systems to keep alive are the ones people like using because they help without getting in the way. Revisit the design after a few weeks in service and ask the users whether the device adds steps, forces awkward motion, or triggers alarms they routinely ignore. If it does, simplify. Replace fragile alignments with more generous guides. Swap a complex sensor for a physical stop if it provides the same protection. Remove decorative indicators that do not change behavior and keep only those that drive action. Sustaining is also about maintainability. Choose standard fasteners, readily available spares, and cleaning methods that fit existing routines. If upkeep requires a specialist or a rare part, the device will drift out of service. Integration with daily management locks and gains. Place the safeguard inside the normal flow of work, so it is activated by doing the job correctly. not by an extra step people must remember. Add the key checks to layered process audits, so supervisors and managers see the device in use during routine Gemba walks and can coach to standard. Tie the main effectiveness metric to the team's visual performance board, so results are reviewed in stand-up meetings. When an abnormal condition is detected, connect the response to an ANDON or simple escalation rule, so help arrives quickly and the problem is contained. Make ownership explicit by naming a primary and secondary owner for each safeguard, with simple weekly tasks that take minutes, not hours. Combining Poka-Yoke with 5S and visual management multiplies the effect. 5S makes error-proofing easier to use and easier to maintain. Sort removes duplicate or obsolete items that confuse selection. Set in order gives each item a labeled home, so the correct tool or part is always at hand and lookalikes are separated. Shine turns cleaning into inspection, revealing wear, misalignment, or damage before failure. Standardize creates the visual and procedural baseline that error-proofing is designed against. Sustain builds the audit cadence that keeps both the environment and the devices reliable over time. Visual management, meanwhile, turns status into something anyone can see at a glance. Use color blocks, shape cues, and large labels to show correct orientation and placement. Show work in process limits and complete kit visuals, so missing items are obvious. Display simple heat maps of recent errors or near misses, so improvement energy targets the right spots. When people can see normal and abnormal instantly, they act sooner and more consistently. Over time, treat your safeguards as a portfolio. Review them quarterly with a short effectiveness and health summary that highlights which devices eliminated a category of defects, which are drifting, and which are candidates for simplification or replication elsewhere. Retire devices that no longer add protection because the underlying process has changed, and reinvest effort in areas with higher risk or cost of failure. Share before and after stories across sites and functions so teams can borrow proven designs rather than reinvent them. Finally, remember that sustaining Poka-Yoke is a cultural practice. Leaders set the tone by thanking teams for raising near misses, by asking what in the process allowed this, instead of who did this, and by funding the small, fast fixes that prevent tomorrow's defects. When documentation is clear, monitoring is routine, adaptation is expected, and lean basics are in place, mistake-proofing remains simple, affordable, and reliable long after launch. Recap of key points and practical application. Tips Poka-Yoke is the practice of designing work so that common slips do not turn into defects. It began in the Toyota production system and is grounded in respect for people and prevention at the source. The central idea is simple. Shape the product, tools, and process so the correct action is the easiest action, and the wrong action is either impossible or immediately visible. Throughout this course, you saw how errors arise from human factors, equipment issues, and unclear instructions, and why it helps to separate a mistake that occurs inside the process from a defect that escapes to the customer. You also saw that a zero defects mindset is not a demand for perfection from individuals. It is a design philosophy that treats every recurring error as a solvable problem. 3 method families give you a practical toolbox. The contact method uses physical attributes such as shape, size, color, or orientation to prevent misuse. The fixed value method ensures a required number of actions or parts occur every time, which prevents omissions and overprocessing. The motion step method enforces the correct sequence, which protects safety and quality where order matters. These methods are strengthened by devices and cues, such as sensors that confirm presence, guides and jigs that locate parts correctly, templates that standardize placement, interlocks that block unsafe or incomplete steps, and visual controls that make status obvious at a glance. Across manufacturing, service, healthcare, and digital work, these same principles apply in different media. A keyed connector on a line, a required field in a form, and a color-coded syringe system are all examples of the same thinking. Good error proofing is simple, affordable, and reliable. Simplicity keeps failure modes low and training light. Affordability speeds experimentation and adoption. Reliability means the safeguard works under real conditions and is hard to bypass during normal work. Strong designs come from the people who do the job. Frontline employees help identify the exact moment a mistake occurs and what kind of barrier would help. Testing and validation turn ideas into proven controls. A short pilot in the real environment with clear success measures and observation of side effects prevents surprises during rollout. Over-engineering is a common trap. If a cardboard template solves the problem, you do not need a camera and software. The best solutions are almost invisible when work is done correctly, and only assert themselves when something goes off standard. Sustaining the gain requires documentation, monitoring, and adaptation. Document the safeguard in standard work at the point of use with clear images of normal and abnormal conditions, the acceptance criteria, and the immediate response plan. Monitor both outcomes and device health. Outcomes show whether the error still occurs and how often. Health checks confirm that sensors detect, jigs align, interlocks actuate, and validations still fire after updates. Expect change. New products, layouts, materials, or screens can invalidate yesterday's fix. A simple management of change routine, supported by quick plan-do-study-act cycles, keeps protection current. Poka-Yoke works best when paired with 5S and visual management. 5S removes clutter that causes confusion, places items where they are needed, and turns cleaning into inspection. Visual management turns status into something anyone can see, which drives faster and more consistent action. Putting this into practice starts with a precise problem statement. Name the specific mistake, the step where it occurs, and the impact if it escapes. Observe the work where it happens and capture the conditions that enable the slip, such as layout, lighting, look-alike parts, screen design, or workload. Select a method that matches the risk. If the issue is the wrong part or orientation, start with a contact solution, such as a keyed fixture, a go or no-go gauge, or a shape template. If the issue is a missing action, use a fixed value approach such as a counter, a kit with dedicated slots, or a form rule that blocks submission until all fields are complete. If the issue is sequence, use a motion step approach, such as an interlock that enforces order, a checklist embedded in the software, or a workstation that unlocks only when the prior step signals completion. Favor geometry first, then simple sensors, then software logic, moving up the complexity ladder only when each lower level cannot give the needed protection. Design for real conditions, not for ideal ones. Assume gloves, glare, noise, vibration, and time pressure. Include tactile and shape cues, so color vision deficiencies do not undermine protection. Make the device easy to clean and maintain with standard fasteners and common spares. Build in a quick daily heartbeat check so users confirm function in seconds at startup. Measure the effect with a short baseline and the same measures during the pilot. If you see false alarms or slowdowns, simplify the trigger or widen tolerances while keeping protection intact. When the safeguard is stable, integrate it into the flow so it engages automatically as part of normal motion. Update standard work, the control plan, and the FMEA. Train with hands-on practice, not a slide deck, and make ownership explicit by naming who inspects, who repairs, and who reviews performance. Keep the culture preventive and learning focused. Treat every detected abnormality as a useful signal, not a personal failure. Thank people for raising near misses. During Gemba walks, leaders should ask whether the device made the right action easier, and whether it prevented or revealed an error early. Review safeguards as a portfolio each quarter. Retire those that no longer add protection, replicate those that eliminated a class of defects, and refine those that cause friction. Share simple one-point lessons with photos so other areas can borrow a proven fix in minutes. If you remember nothing else, remember this sequence. Clarify the mistake and when it happens. Choose the lowest cost method that removes or exposes the error at the earliest possible moment. Co-design with the people who do the work. Pilot, measure, and refine until it is simple, affordable, and reliable. Integrate it into standard work, 5S, and visual management, so it becomes the natural way of working. Then keep watching and improving as conditions change. Done this way, Poka-Yoke reduces defects, saves time, and lowers stress, while protecting customers and making good work easier to do.